All right. Hi. Okay. So we're going to do, I think maybe this is why. Mhm. I don't know. All right. We're going to talk a little bit about logs. So when we talked the other day, we figured out that if you have, and I'm sorry, the light isn't as best as it could be. We know that if we have like y equals the natural log of x, that its derivative is 1 over x. So I want to think about this in terms of the graph. So we know the natural log of x looks like this. Domain is x is greater than 0. X is greater than 0. And range is all real numbers. And then if we look at the graph of y equals 1 over x, we get this, where its domain is all real numbers such that x can't be 0, and its range is all real numbers such that y can't be 0, right? So what we're saying is when you look at this graph and we talk about its derivative, as x approaches 0, these are getting to be very, very positive, really positive values. And then as x gets bigger and bigger and bigger, they're going closer and closer and closer to 0. We're also noticing that the natural log of x is not defined here, right? Its domain is x is greater than 0, which means this whole part of the graph over here can't be included. So when we're talking about the natural log of x, or logs in general, it's the one case where the original equation or the original function, hi, I'm making a movie.
Am I interfering?
Nope.
I can go upstairs and watch the news.
No, come on in. I can also go in the other room and finish it.
No, I'll leave you here and I'll go upstairs and watch the news.
No, you don't need to go upstairs.
No mind. Finish this and then yell when you're done.
How was your nap?
It was nice.
Good.
How'd you know I was napping?
Well, it was nice and quiet.
Oh, okay. Yeah.
One of the neighbors came by and dropped off some, see, now I've forgotten all of it, some walnut bread.
Oh, okay. And somebody else had left some at the door when I got home.
Yeah, I
so
saw that.
When you finish, let me know.
All right, I just need like 5 or 10 minutes.
Okay.
All right, so we know that the natural log, or when we talk about logs, it's the one case where when we have the function, its derivative, just as its own on a function, is less restrictive in the domain than the original function. So when I look at this, it implies that its domain is x is greater than 0, where this one does not imply that domain. So anywhere else, like if you have a cubic or a quartic, or like a polynomial, you take the derivative of it, the derivative will have the same domain, except with logs. So when you're doing log functions, if you take a derivative, so if I give you y equals the natural log of x and ask you for the derivative, your answer should be 1 over x, and then you have to explicitly state the domain, because this function by itself does not imply that restrictive domain. All right. Mostly you're going to see this at places where it's already restricted this domain and you're like, why is that in there? Well, that's why it's in there. Okay. So that's one piece. And then just know, if you get something like y equals log base 6 of 4x minus 7, that when you take the derivative of that, it's going to be 1 over 4x minus 7 times the natural log of 6 times 4 on the top. And then you're going to state x is greater than 7/4, right? So remember, when you're finding the domain of a log function, you just know that argument has to be greater than 0. Okay, that's part 1. Part 2, we're going to use the properties of logs to help make more complicated problems simpler. So that's the beauty of logarithms, is you can take things. So remember our properties of logs from last year. We know that the log of m times n is the log of m plus the log of n. And I know the log of m over n is the log of m minus the log of n. And the log of m to the n is n times the log of m. I call that the slingshot rule. Okay, so those properties of logs, when you look at them, what they do is they take a multiplication problem and turn it into an addition problem, or a division problem and turning it into a subtraction problem, or a power problem that turns into a multiplication problem. So we're simplifying problems. So what happens is if you have, let's say, an equation like this, and I'm asking you to find a derivative. So if you just take this and take the derivative, it's going to be 1 over that whole thing, right? The natural log of something, it's 1 over the fifth root of that whole thing times the derivative of this thing, right? Well, this is really this to the 1/5. So it'll be 1/5 times that whole thing to the negative 4/5 times the derivative of this thing, right? Which now needs a product rule and a quotient rule and ugh, right? That is a big, old, ugly problem. But what we can do is use the properties of logs to rewrite this into a simpler problem. So this is still this whole thing to the 1/5. So I'm going to start with my slingshot rule. This is 1/5 times the natural log of x plus 2 cubed times x minus 5 squared all over x plus 3 to the 7th. And now I'm going to use these first two properties to break this down. So this is going to be 1/5 times the natural log of x plus 2 cubed plus, I'm going to put the 1/5 out front, the natural log of x minus 5 squared minus the natural log of x plus 3 to the 7th. I'm going to slingshot again and distribute the 1/5. So this will be 3/5 times the natural log of x plus 2 plus 2/5 times the natural log of x minus 5 minus 7/5 times the natural log of x plus 3. Now, that's my y. So to take the derivative of this is pretty simple, certainly compared to this. Done. Okay, so this is a way easier problem to solve than this. So what we do then is we recognize that we can use those properties even if it's not originally written that way. So if I have something like y equals, let's just say the square root of, 4x minus 9 cubed times cosine squared of x all over 3x plus 5 to the 7th, right? Like whatever these things are. Inverse, well, we haven't done an inverse trig yet, but, throw whatever e to the x and all that kind of stuff in there. So now I can recognize that this is really complicated with multiplication, division, powers. So I'm going to use those properties of logs. So now what I'm going to do is just take the natural log of both sides. And then I can leave this side alone for a minute and use this. So this is all to the 1/2. So this is 3/2 times the natural log of 4x minus 9 plus 2/2. So that's just going to be cosine x minus, I'm going to call that a 7. I can't read my own handwriting. 7/2 times 3x plus 5 is the natural log of y. So now I'm going to take the derivative of both sides. Implicit differentiation, don't forget. So over here, I'm going to get 1 over y dy dx equals, derivative of this will be 3 over 2 times 4x minus 9. So it's 1 over this, the 3/2, 1 over this, don't forget, times the derivative of the inside, minus sine x, minus, now I've got 7. Oh, this is the natural log. I dropped my natural log. Sorry. So this will be 1 over cosine x times the derivative of cosine x, which is negative sine x, minus 7 over 2. This is going to be 1 over 3x plus 5 times 3. So now, remember, I want to solve for this. So I'm going to multiply both sides by y times this whole thing, which is, let's see, 12 over 2. That's 6 over 4x minus 9 minus sine over cosine is tangent. minus 21 over 2 times the quantity 3x plus 5. And that's a good answer. Now, if they say write your answer in terms of x, then I'm going to have to substitute this in for y. So just recognize sometimes, and it'll come up as a multiple choice question a lot, if you are rewriting it, that this final answer, if it doesn't say that, it's okay to leave it like this, right? Don't simplify unless you have to. But if they do, then we could rewrite it times, and then this whole thing in here. Okay, so that's a technique called logarithmic differentiation. Now, in general, logarithmic differentiation is a technique that you can use to take a really complicated problem and make it simpler. You don't have to, though, right? You could do this whole derivative out, and if you do it right and don't screw anything up, you should be fine. The only time you really need to use it is if you have something that's in the form of something like this, where you've got y equals x to the x. Now, this is not a power function, right? And it's not an exponential function because there's a variable here and a variable here, right? So when you have something in the form of one function raised to another function, the only way you're going to be able to do that is using logarithmic differentiation. So let's say, well, let me do something like, let's say we have x to the sine x. Okay, so now what I'm going to do is take the natural log of both sides and then slingshot my exponent. So now on this side, I have a product rule. So I've gotten rid of that exponent and I've turned it into a product. So now I've got the natural log of y equals sine x times the natural log of x. So I'm going to take the derivative, 1 over y dy dx. Remember, now I need a product rule. So it's going to be the derivative of the first times the second plus the derivative of the second times the first. So my final answer would be x to the sine x times the cosine x times the natural log of x plus sine x over x. So anytime you get a function raised to a function, you got to go to logarithmic differentiation. All right, I think that's it. Let me make sure I covered everything I needed to cover. I did. And then you got some problems in your textbook you're going to do for homework. Those are posted in Google Classroom. Sorry to miss you yet again tomorrow. I will see you guys on Wednesday.